So the wrist rockets on the Mark II suit for the right arm, we want to improve them. We want them to fly straighter. We've been looking at a lot of different techniques to do that, but we haven't necessarily found kind of our golden solution. What I was mainly thinking of doing was essentially using an external motor to actually just spin the rocket up really fast in the barrel, and that would impart a gyroscopic stability factor so that when it flies, it has a lot more resistance to any sort of like deviation forces while it's flying. And that's kind of where this general project direction has been going recently. But the most recent, successful attempt I kind of did with a gear train. As we know from that test, didn't work as expected. It improved the actual stability factor from the same test without the spinning. Clearly the actual gyroscopic stability factor enhances the behavior, but it doesn't enhance it to the extent that we want. We want almost linear motion during flight. We've kind of optimized a little bit on the actual fluid dynamic side, and now we're focusing on the optimization of the actual gyroscopic mechanism. I was thinking of what's the main issue with the gear train system? And it has to do with the fact that there's a ton of energy losses in that transmission. Sound itself is a form of energy loss, friction, all that stuff that kind of just reduces the performance of the system. And that motor itself, the brushless motor that I'm using, that can produce a very high RPM. I think it's around like 1500 RPM. If you actually do the gyroscopic stability math, if we assume a perfect transmission from 1500 through our gear train to the rocket, even that doesn't really give us the best gyroscopic stability factor, and obviously we're not getting 100% full efficiency in the transmission. That makes a lot of sense why we're seeing not fully linear flight even when we impart the spin. Clearly we need more RPMs. That's the goal. We need more RPMs on the rocket so it spins faster, and that should help the actual flight path be a lot straighter. Of course, assuming that we have kind of your foundational aerodynamic factors that we've talked about a while ago. However, with the kind of current geometry of the system and all the other subsystems that are there, it's really hard to kind of stick a motor right behind the rocket while still kind of using the space that I have for myself. With that in mind, there's a couple of bearings that I have around the rocket that aim to reduce the friction that the rocket experiences when it's spinning from the gear train. In an ideal world, imagine if the bearings could actually spin the rocket instead of just being passive components that just help with friction loss. If you're familiar with frameless inrunner motors, they kind of strip away all the extra stuff that motors normally have, and what you're left with is your outside stator and then your inside rotor. And those guys basically create this like donut looking thing where you still have a hollow inside of your motor where you could put something through, our rocket for example. So that's kind of where my head's been at recently. You've probably seen me talk about this kind of mechanism in previous videos. I've been calling it the direct drive rocket, which kind of makes sense because we're directly driving it from the motor. We can easily assume that that's much more efficient than a gear train going through the arm. Basically all the motors that I've looked for and found and kind of quoted and everything, the actual sizes are like basically either too small or too big, and the size in between is the size that I need. So there's like basically nothing that kind of exists within the size domain that I want. So we're kind of in like this weird space where it's like I can prioritize the system to the point where I redesign everything to accommodate for like some off-the-shelf motor, or hear me out, we design our own motor that essentially fills that gap that we've been missing and gets us the performance that we want by optimizing for RPM versus torque. And a lot of these motors out there kind of optimize more for torque because they're meant for like low speed actuation of like robots and stuff like that. We're in a weird space. We need a high RPM motor that's small. Those exist a lot for drones, but they don't necessarily exist in the frameless form factor. So might as well learn how to make freaking custom motors, right? That's what we need to do. So how do we even go about, making a custom motor? The first thing we need to do is kind of understand how they work. Looking at kind of our two different areas of motor control, we have a brush motor and a brushless motor. But basically, the brushed motor operates on a DC input, whereas a brushless motor kind of operates on AC. The idea is that the brushless motor has three-phase AC input, creating a rotating magnetic field through the actual stator, and then that influences your rotor, which has permanent magnets on there, causing that to spin. If you look kind of like at the basic fundamentals of our brushless motor, there's really only two parts that we need to design. We need to design a stator, which gets the name from the fact that it's static, stator static, and that part is what actually creates our rotating magnetic field. And then we need to design our rotor, which rotates, rotor rotates, and that's what gets influenced by the magnetic field to then rotate and spin whatever we want, which in our case would be the rocket. So as we look to design those two main parts, the first few considerations we need to have going into it is going to be the size constraint. We can kind of start designing the stator and rotor to give us an outer diameter and inner diameter that fits well within our constraints. With the stator itself, the geometry is pretty interesting. You have your stator teeth, and those teeth have the coils wrapped around them, but they also dictate how well the actual magnetic flux lines kind of flow through the stator itself. So if they're too small, or if we have too many kind of magnetic flux lines flowing through them, what you end up getting is stator tooth saturation, which basically means that you have so much magnetic flux that it's kind of leaking outside of the stator, and you lose efficiency, and it kind of messes up the whole process. So you need to design them in a way such that there's enough material there that it kind of correlates well with how much magnetic flux you have flowing through them. You want the amount of stator teeth you have to be divisible by 3. You want to be able to have an even amount of each of your three-phase AC coils. to make sure that the magnetic field that rotates through there is uniform and can actually go in like a cycle, right? And kind of once we have that design down, we kind of selected how many teeth we want, how many slots we want. We actually do want to throw this into a simulation to make sure that we're not actually reaching the saturation that I talked about. When simulating the stator, we actually need to put the rotor in there as well with the permanent magnets. Otherwise, we won't see how the magnetic fields interact with the stator teeth. And with the rotor, that design there has been kind of modified so that it couples with the rocket. And I designed the rotor in a way that it only has 6 magnets, and that makes it a 6-pole rotor. If you have less magnets in the rotor, you can drive it at a higher RPM, because that means you can actually control it at a larger electrical frequency. So ideally, we could do 2, but we want to stay in a reasonable range. If I spin it too fast, this thing's going to tear itself apart because it's a DIY motor. So we need to have some kind of comfortable RPM range where we want the speed that we need for the rocket, but not too fast that it's going to blow up in my face. With the rotor, when you put the permanent magnets on it, you want them to have opposite poles as you go around, so north, south. And that actually allows you to see the flux path through the stator. You should see the flux lines going in one tooth, coming out the other one on the north and south pairs on the rotor. If we had too strong of magnets, we'd probably see leakage. If we saw too weak of a magnets, we probably wouldn't see enough, magnetic field saturation. We kind of want to be more on the saturated side where we have a lot of flux going through it, because that means we're kind of pulling more performance out of the system. So before we add the coils, this kind of base analysis we're doing here with the rotor, the permanent magnets, and the stator, that kind of gives us some insight into what's called the cogging torque. So there's going to be a little bit of a tendency for the rotor to want to align to some position because of just the passive magnetic field that those permanent magnets create. And that creates some opposition torque to the actual movement that you want, because basically it kind of cogs and stays at a position naturally. And when you evaluate the actual output torque of the system, you want to account for the cogging torque and make sure that it's not overpowering. If the permanent magnets on the rotor create a cogging torque that's higher than the actual torque created from adding the coils, then you're left with a motor that basically just heats up and doesn't work. And once we get our cogging torque, we can then kind of start adding the coils. That changes the whole game. Basically what we get is ABC kind of around the stator, but then we alternate some of the polarities in a periodic way such that by the end you have a perfectly uniform kind of alternating polarity of your coils around the stator. And that's how you get your uniform rotating magnetic field as you actually add your 3-phase AC. So there's a lot of experimentation kind of analysis you have to do to find out the optimal running point. But basically what you do is you do a kind of static rotor sweep where you sweep the magnetic field rotating around the stator, and that gives you kind of a peak torque at some point, and that's going to be your offset point. That's the point where you get the highest kind of differential between the actual magnetic field position that you've rotated and the rotor itself. And you want to start with that because that means it's going to kick off your rotor at the highest torque. And when you rotate the magnetic field, your rotor is basically chasing that offset. So now instead of just spinning the magnetic field, we start the magnetic field offset, and then we start actually rotating the rotor as well, while also rotating the magnetic field as the rotor moves. And that'll kind of simulate the real life performance of the system, right? As we start rotating the rotor and then also rotating the magnetic field, we get a more realistic torque sweep on the output, which we can then use to kind of understand if the motor is going to behave in a more expected way. The main thing I'm looking for is to make sure that the torque itself doesn't dip below 0, because that means it basically wants to go in the opposite direction at some point, which is not good. We're looking for just a constant positive torque. It's going to have kind of peaks and valleys because it's not a perfect motor, it's not a perfect system, but it should be all positive, which is what we're seeing, which is great. So we're seeing an all positive kind of sinusoidal torque curve. It should be enough to get the rotor to move in a way that we want to. I don't know if we're going to get the RPM yet, but we're just getting started, so it's okay. But we also want to make sure to actually subtract the cogging torque from the output torque. That output torque kind of assumes everything, right? That's including the cogging torque and all this other stuff. So we want to make sure that we're canceling that out so that we know if the motor is actually going to behave like a motor. The simulation is kind of indicating that we should see some motion. So I went ahead and ordered the parts. I ordered some stators, I ordered a rotor, I ordered like the little back iron to kind of combine everything together. But I think we'll design a couple of test beds for the motor to really validate the system. We want to make sure at least it's giving us some more of a significant RPM that's actually going to potentially stabilize the rocket. We don't want to be seeing less RPMs in the gear train because that defeats the whole purpose of the project. So we're going to look into that. We still have the other side, the left one, that we can still test the old system on. So we're not necessarily scrapping that entirely. We know it works to an extent, so we maybe can see some more improvements there first before transitioning into this more complex design that may be a little bit more difficult to get to a more functional state, whereas the other one kind of already works. So, don't want to really destroy the progress made there. So that's where we're going there. A couple of updates coming soon, so stay on the lookout for those. See you guys.